Welcome back. Today we will begin Chapter 9 of Pre-Calculus Made Difficult. And this is the chapter in which we begin trigonometry proper. In the previous video, I said that we would build a kind of trigonometry machine which will ultimately allow us to take any triangle whatsoever, and once we know enough information to determine the triangle, to determine its shape and size, and we could get that with something like angle, side, angle, or side, angle, side, or side, 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 or whatever, any of the determining trios that we discussed in the last video. Once we have three pieces of information that determine a triangle, our trigonometry machine will allow us to feed that information into it, and it will produce the remaining parts of the triangle. Like in this case, it would give us the remaining three angles. Or if we knew angle, side, angle, the trigonometry machine would allow us to find the lengths of the remaining sides, and of course the final angle. Anyway, in Chapter 9, we will not build the complete trigonometry machine, but we will build the core of it. And that core will work for any right triangle in particular. So our goal is to build a trigonometry machine for right triangles specifically in this chapter. And you might think, well, that's a little disappointing, but it's not that disappointing. Remember back in the first video when I mentioned that any polygon whatsoever, any figure with straight sides, can be triangulated, can be chopped into triangles, and that this is one reason why trigonometry is important in the first place. We can reduce any problem about polygons to a series of problems about mere triangles. Okay, you know that, but we can actually carry this reduction further, because given any triangle, we can always drop a perpendicular from a vertex to the opposite side and cut the triangle into two right triangles. So any polygon can be reduced to triangles, and any question about triangles can be reduced to right triangles. So if I wanted to, I could take this polygon picture over here and cut it into right triangles. So that in a sense, if we understand right triangles, we understand all polygons, all figures that don't involve curves. Once we have curves in the picture, we generally have to bring in calculus. But so long as we don't have curves, we should be able to reduce everything to mere right triangles. Okay, we ended the last video with a quick discussion of similarity. Similar figures being two figures with the same shape, though not necessarily the same size. They're scale models of one another, like these two triangles, or these two circles, or these two owls. And the crucial fact about similar figures is that all their corresponding ratios are the same. So for example, on this pair of similar triangles, whatever the ratio of this side is to this side, for the sake of argument, let's say it's 5:4, we will have the exact same ratio of lengths on this larger but similar triangle. The lengths, of course, are not 5 and 4, but they will be in that ratio 5:4. So for example, if this side has length 10, then this side would have to have length 8, so that the ratio is maintained. 5:4 as 10:8. Or if we look at this similar pair of owls, if the large owl's height is 20 units, and the distance between its pupils is 3 units, then that same 20:3 ratio is going to hold on the smaller but similar owl, even though the individual measurements will differ. For example, if the small owl is 11 units high, then what is its pupillary distance? Well, we could determine that by giving it a name like x, and then setting up a proportion. We know that x is to 11 as 3 is to 20. This proportion holds thanks to the similarity of the owls, and if we solve for x here, we get that x is 33/20, or if you prefer, 1.65. So that's why we care about similar figures. All the proportions must be the same. If we know a certain ratio of lengths on one, we know that the other one will exhibit the exact same ratio of lengths, even though the individual lengths will change a lot. All right, let's let those owls fly away. But let me remind you something about these circles, which are much simpler figures than owls. All circles are similar to one another. These two circles are just scale models of one another. I could blow the little one up to get the big one, or shrink the big one down to get the little one. All circles are similar. There are no such thing as circles that have different shapes. That's in complete contrast to something like triangles. These two triangles have the same shape, but it's a very different shape than, say, this triangle has, though not all triangles are similar. But I mentioned the fact that all circles are similar so that we can think of the set of all circles as being one big family. And if we pick any one circle and measure the ratio of two lengths related to that circle, that ratio will be the same on all of the circles that have ever existed or ever will exist. Provided, of course, we were talking about genuine geometric circles and not my crude irregular drawings here. Well, that's all true, but there just aren't that many lengths of interest on a circle. I mean, we can talk about its circumference, that's an important length, and we can talk about its diameter, or equivalently its radius, which is just half the diameter, that's an important length. But that's it. Those are the only interesting lengths on a circle. Even so, it is true that if we took a circle and measured its circumference and then measured its diameter and took that ratio, circumference to diameter, whatever that was on this circle, we would get the exact same ratio on this circle and this circle and this circle. And every circle would have that same ratio because all circles are similar. Well, what does that mean? What do I mean by the ratio of the circumference to the diameter? If we're thinking numerically, that just means how many times does the diameter go into the circumference? That answer is going to be the same on every circle that exists. So if we knew what it was for one circle, we would know what it is for every circle. And we can get a crude estimate for the value of that ratio just with a tape measure. We could measure the diameter and then take our tape measure and lay it off on this curved surface there and say, okay, it goes in once, and then it goes in a second time, and then it goes in a third time, and then there's a little bit left over. So it looks like this ratio is a bit more than 3. And that will be true on this circle, and 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 all of them. And because circles are so ubiquitous, and because this is the only ratio of lengths of any interest on a circle, mathematicians found that they had many, many, many occasions to refer to this particular ratio. And once upon a time, whenever they referred to it in their writing, they would have to say, the ratio of the circumference to the diameter in all circles. And that's a very unwieldy phrase to say over and over again. After a while, people got sick of writing that and saying it, and so they decided, let's not say this phrase over and over again, let's just come up with a single symbol for the common ratio of the circumference to the diameter in all circles. And you know what that symbol is? It's pi. That's what pi is. Pi is not primarily the irrational number 3.141592653, etc., etc. Rather, the actual definition of pi is that pi is a ratio. It's the ratio of circumference to diameter that holds in all circles. Such a thing exists because all circles are similar. That's the reason we have such a thing as pi in the first place. And then you can ask the question, well, what is the numerical value of pi? We can see physically that it's a little bit more than 3, but how do we know that it's actually more like 3.14159, etc.? Well, that's a long story and an interesting one, but not one I have time to tell you here. Although trigonometry is very helpful in explaining that story. But I bring it up here because we are about to define some other special ratios that have a great deal in common with the way that we define pi. It's just that they're connected not to this vast family of all circles, but rather to certain families of right triangles that are all similar to one another. Let me shrink this stuff down, just as a little reminder to ourselves that all circles are similar, which in turn implies that this ratio of lengths, circumference to diameter, is the same for all circles. In other words, pi exists. It's well defined. That's the definition of pi. Now, let's talk about similarity in the context of triangles. As we said before, not all triangles are similar, obviously, but some of them are. And we saw in the previous video that angle is a similarity criterion for triangles. In other words, if I have a pair of triangles and I know that they agree on a pair of angles, then in fact these two triangles must be similar. They're just scale models of one another. All their corresponding ratios are equal. Well, that's kind of interesting because that means that the world of triangles consists of lots of different families of similar figures. For example, suppose I have a right triangle that also contains a 30-degree angle. So I know two angles in this triangle. So the knowledge of those two angles, that alone is enough to determine the shape of the triangle. and any other right triangle with a 30-degree angle in it must be similar to my original triangle because they agree on angle. They both have a 30-degree angle, they both have a 90-degree angle, so they must be similar triangles, scale models of one another. All their ratios are the same. Well, of course, there are infinitely many triangles of this sort, right triangles with a 30-degree angle in them. And they're all similar, just like all circles are similar. So you have to imagine this vast family of right triangles with a 30-degree angle, or as we sometimes call them, 30, 60, 90 triangles, because they all have a 60-degree angle as well. And all right triangles with a 30-degree angle are similar. And that implies that the ratio of corresponding sides will be the same on any two of these triangles. And the same story holds for, say, all right triangles with a 22-degree angle. They are all similar to one another. And again, by angle. Same story here, by angle, because all such triangles have a right angle and they all have a 22-degree angle. And in fact, they all have a 68-degree angle as well. So if we imagine all the many triangles of this sort, all right triangles with a 22-degree angle, the corresponding ratios on all of them must be the same. Just like in the case of circles, they're all similar, so circumference to diameter is the same. The same kind of thing holds with right triangles with a 22-degree angle. They're all similar, so if we looked at, say, the ratio of the hypotenuse to the side opposite the 22-degree angle, so that hypotenuse to that side, it's going to be the same for all of these right triangles with 22-degree angles in them. And I am surely reiterating myself far more than is necessary here, but I'm just trying to impress upon you where this all comes from, because people sometimes get lost once they get into the thickets of trigonometry, and I don't want that to happen to you. I want you to see that all of this kind of flows naturally from very simple geometric ideas. But I think you get the point. If we looked at all right triangles that have a 17-degree angle in them, they would all be similar. If we looked at all right triangles that had a 45-degree angle in them, they would be similar, and so on and so forth. So we would have not just one family, like we did with circles, not just one family of right triangles, but lots of big families of right triangles. In fact, we'd have infinitely many of them, because we'd have not just all right triangles with a 22-degree angle, we'd have all the right triangles with a 22.1734-degree angle in them. They're all similar, and they would all make up a giant infinite family, and all of their corresponding ratios would be equal to one another. Now, we don't want to talk about each one of those families separately. So what I'm going to consider next is a slight abstraction of this idea. Let's say I've got a right triangle, and I know one of the acute angles in it. But rather than specifying it's 30 degrees, or it's 22 degrees, or it's 17 degrees, I'm just going to say, let's call it theta. If that's a new symbol to you, then good, you are expanding your Greek alphabet that much more. Theta, as you will see in this course and courses to come, theta is very frequently used for angles. So this might be the first time you're meeting it, but it will not be the last. Anyway, we're going to consider a right triangle that has one other known angle, theta. Well, it's not the only right triangle with that known angle, and we want to consider the vast infinite family of all right triangles containing angle theta, whatever it may be in a given situation. 30 degrees, 22 degrees, 17 degrees, 84 degrees. We don't care. Whatever we're talking about, we can consider the whole family of all triangles, all right triangles that contain that angle, and we know that all of them are similar, and we know why they are similar by the angle-angle similarity criterion. Well, that means that corresponding length ratios are equal for all such triangles, all right triangles containing angle theta. Now, note how similar this is to the case of circles, but note also how different it is. In the case of all circles were similar, so all the corresponding length ratios were equal. But we said there was really only one interesting ratio of lengths on circles, circumference to diameter. That's the same on all circles, and so we just have one symbol for it, namely pi. But here, for any given value of theta, there are lots of different length ratios we could consider. And to explain what they are, let me introduce some terminology that we tend to use in trigonometry. When we're talking about a right triangle with some given acute angle theta, of course, we know the name for the long side, the one across from the right angle. We call that the hypotenuse. But we have specific names that we tend to use for the legs of such a triangle. We're concentrating on some particular angle theta, while the leg that is opposite theta we just call the opposite leg, which I will abbreviate here, OPP. And then the other leg, the one that is next to the given angle theta, or to use a fancier word, that is adjacent to angle theta, well, we call that the adjacent leg. So I will abbreviate that ADJ for adjacent. And remember, when we talk about opposite or adjacent, that's always relative to a specific acute angle. So if we were talking about this other acute angle, then this side would be the side opposite to that angle, and this side would be the side adjacent to that red angle. So opposite and adjacent are always meant relative to some pre-specified angle. Anyway, so if we consider our right triangle containing the acute angle theta, then considering everything relative to theta, there are three lengths of interest: the hypotenuse, the opposite leg, and the adjacent leg. And we could consider the ratio of any one of those three sides to any one of the two others. For example, we could consider this ratio, the opposite to the hypotenuse, this length to this length. If we have any other right triangle with the given angle theta, then that ratio, opposite to hypotenuse, is the same on the one triangle as it is on the other. But we could consider other ratios as well. For example, we could have considered, say, the opposite side to the adjacent side, this leg to this leg. That ratio will be the same in all right triangles that contain angle theta. Well, those are the only two ratios where we start with the opposite on the top, but we could have others like adjacent to hypotenuse or adjacent to opposite. And what have I left out? I've left out the cases where hypotenuse is on top. So we could have hypotenuse to adjacent or hypotenuse to opposite. And that's it. Those are the 6 ratios of interest that are the same for all right triangles that contain some specified acute angle. So unlike circles where there's really only one ratio of interest, there are 6 of them for each vast family of right triangles. And this is one of the reasons why you have a whole course in trigonometry and not just a few minutes in which you define the concept of pi. Well, each one of these 6 ratios has a name. I'll introduce them all in turn. Today we are just going to talk about these first 3. The latter 3 are not as interesting because they're just the reciprocals of these 3. For example, adjacent to opposite is not all that exciting once you know about opposite to adjacent. So all the action takes place with these 3 ratios. So let me go ahead and define them more carefully and introduce you to their formal names. So let's have some definitions. First, this strange symbol. It looks like sin, but it's actually short, though not much shorter, for the word it is actually standing for, which is sine. It's a strange word with a very strange etymology, but all we need to know about it is that the sine of theta is defined to be the opposite over the hypotenuse, where again, of course, opposite means opposite the angle theta in any right triangle that contains theta. I have the definitions written out with full care in the book. Here I'm giving you the abbreviated versions so that we can concentrate on the essentials. So that ratio of opposite to hypotenuse, which will be the same for all right triangles containing theta, we call it the sine of theta. Then we have another ratio we are going to consider, namely the adjacent side to the hypotenuse. So this guy to the hypotenuse. We call that one, we write it like this, and that is short for the full name, which is the way we pronounce it, which is the cosine of theta. But we just write it cos theta. But we say cosine of theta. Cosine of theta is that adjacent to hypotenuse ratio. And then I will introduce one more, and then we will dwell on this quite a bit. The last one I'm going to introduce today is the opposite to adjacent ratio. And we call that the tangent of theta, which we abbreviate tan theta. So again, that is short for the word tangent, and I'll explain what that has to do with tangents as in tangent lines in the next chapter. Now we will put these to use very soon, but first I want to show you how to remember them, because if you haven't seen these before, no doubt you are thinking, how am I going to remember which one is which? That seems like an ugly thing to memorize. Well, the famous old mnemonic is this: SOH CAH TOA, and SOH CAH TOA, name of the ancient god of trigonometry. And when you are doing trigonometry, if you forget anything about these 3 key ratios, you just call his name. Oh, great SOH CAH TOA, remind me which ratio I'm interested in, and his name itself will answer back to you, and you will be enlightened. For what does his name mean? So tells us about the definition of sine. There's the S. there's the O, there's the H. Sine is opposite over hypotenuse. Ca tells us about cosine. Cosine with a C is adjacent with an A over hypotenuse with an H. And of course, toa tells us about tangent with a T is opposite with an O over adjacent with an A. So if you remember the great god SOH CAH TOA's name, you will never forget these ratios. And now, let's get into some specific numerical examples. After all, when we did the analogous stuff with circles, we said, well, all right, I've got a circle. I know that the circumference to diameter is the same on all circles because all circles are similar. So how many times does the diameter go into the circumference? Well, measure it on one, and it's as good as measuring it on any. Here's the diameter. Lay it off once, twice, 3 times, and a little bit. So we knew that this ratio, circumference to diameter, was going to be a little bigger than 3. And we gave that ratio a name. We called it pi. So in fact, we could say that pi, which was once a new idea to you, is defined as the circumference over the diameter, and that is about 3 plus a bit. And then, of course, you were told that it's actually about 3.14159, etc. We want to consider something similar with these new ratios that we're talking about, sine, cosine, and tangent. But of course, the values of these ratios depend on the specific angle we're working with. If I have a right triangle with a 40-degree angle and a right triangle with a 12-degree angle, I can see even from my crude sketches that the sine of 40 degrees and the sine of 12 degrees will be very, very different, because the sine of any acute angle is going to be that opposite to hypotenuse ratio. So the sine of 40 degrees is the opposite divided by the hypotenuse. What's that ratio going to be? Well, in this case, the opposite looks like maybe it's about a little more than half of the hypotenuse. So based on my extremely bad drawing, I'm at least pretty confident in saying that the sine of 40 degrees is more than a half, whereas over here, if I wanted to talk about the sine of 12 degrees, well, again, so sine is opposite over hypotenuse. That's the ratio of this opposite leg to this very long hypotenuse. So we've got the ratio of something very small to something very big. So whatever the sine of 12 degrees is, it's going to be small. What proportion of the hypotenuse is taken up by that opposite leg? Maybe 10% or something like that? So who knows? Maybe a tenth. We'll be able to nail down the actual numerical values of these things soon. For now, I'm just pointing out that they're very different depending on what the angle we're dealing with is. And in fact, just as you can look up the numerical value of pi to whatever degree of accuracy you like, you can look up the numerical values of sine of 40 degrees or sine of 12. In fact, if I enter these things on my calculator, I find that the sine of 40 degrees is about 0.6428, while the sine of 12 degrees is about 0.2079. The moral of the story being, don't rely on drawings to get decent estimates of sine, cosine, and tangent. You can get a better estimate, of course, if you use a ruler and protractor and all that. All I said of sine 40 was that it was going to be bigger than a half, and it is, about 0.6. And all I guessed of sine 12 was it was much smaller than that, maybe around a tenth. Well, it is much smaller than that, but it's more like 2/10. And truth be told, for most values of theta, we're going to have to settle for approximate values of sine, cosine, and tangent. In the old days, you would have looked up things like this on a table, and anyone taking a trig class would have had a trigonometric table to work with. And nowadays, of course, we just use a scientific calculator to get those values. And it's a very interesting question as to how those values were come up with in the first place, just like the question of how did we get the first 3 or 5 or 10 or a million or however many decimal places of pi you're interested in. How did we get those 4 decimal places? Well, maybe we'll talk about that later in the course, but for now I want to show you that for certain very special angles, we actually can get exact values of sine, cosine, and tangent. And I want to show you those next and show you how it's actually fairly easy to remember those special values and how to rederive them if you ever forget them. And then we will be ready to learn how to use the right triangle trigonometry machine at last. But let's talk about those special values first, because they will come up again and again and again and again in this course and your calculus classes and your physics classes and your chemistry classes. So let's make sure you understand them well the first time you see them. All right, now we've got a little space. Let's talk about our special angles. There are really only 3 of them at this point: 30 degrees, 45 degrees, and 60 degrees. for these three angles, we can get exact values for sine, cosine, tangent. We don't have to round it to a few decimal places, and we can understand exactly where they came from. The reason why we can do that is because they correspond to very nice triangles. I'm going to start with 30 degrees, because if we have a right triangle with a 30-degree angle, then that right triangle must also have a 60-degree angle, so that everything adds up to 180. So we'll actually take care of two things at once. So here's a right triangle with a 30-degree angle here, and its complement, a 60-degree angle here. By the way, that word complement is an important one. I know I discussed this in the book, but I haven't mentioned it in the lectures yet. So just a reminder, the complement of any acute angle is just whatever we have to add to that angle to bring it up to 90 degrees. So for example, if we have a 20-degree angle, then when we take its complement, we get 70 degrees. We would say that 20 degrees and 70 degrees are complementary angles because together they add up to a right angle. They complement one another. Similarly, if we had a 35-degree angle and we take its complement, then we get a 55-degree angle. 35 degrees and 55 degrees are complementary angles because, again, they add up to 90 degrees. They add up to a right angle. A 1-degree angle's complement is, of course, 89 degrees. And these run both ways, of course. The complement of an 89-degree angle is a 1-degree angle. Complements come up all the time in this particular subject because if we are dealing with a right triangle, then we've already used up 90 of the 180 degrees. That means the other two angles, the two acute angles, have to add up to the other 90 degrees. That means these acute angles are necessarily complements of one another, like 60 and 30, or the complement of 45 degrees is also 45 degrees, or the complement of 10 degrees is 80 degrees. You get the idea. Anyway, we've got our 30-degree angle, which is the one I said I was going to be interested in, and its complement of 60 degrees, which comes along for the ride. Now, I claim that we can figure out the sine, cosine, and tangent of 30 degrees exactly, and we don't have to go consult a table or a calculator. The key is the idea that those ratios are the same on any 30, 60, 90 triangle by angle-angle similarity. So it doesn't matter what size we're talking about. I could look at that triangle, or I could look at this triangle. All the ratios of the corresponding sides are going to be the same. So if I'm interested in, say, the sine of 30 degrees, oh great SOH CAH TOA, what does that mean? Sine, so opposite over hypotenuse. I'm looking at the ratio of the opposite leg to the hypotenuse, whether I'm looking at this triangle or this triangle. It's the same ratio. So it doesn't matter how large or small my triangle is. It's just the ratios that matter. That's going to be important for us in a moment. Now, the key geometric idea that is going to allow us to compute sine of 30 degrees exactly is this. Any 30, 60, 90 triangle like this is, and this is obvious once you think about it, exactly half of an equilateral triangle. Because if I reflect that original triangle over this side, well, what happens? I get 60 degrees here, I get another 30 degrees here, and another right angle there. So I have a triangle whose angles are 60 degrees, and 60 degrees, because it's 30 plus 30. Well, as you know from basic geometry, if the angles are all equal, namely 60 degrees, then the sides are all equal too. So this is an equilateral triangle. That's important to us because it tells me that this side of the equilateral triangle, which is the hypotenuse of our original 30, 60, 90 triangle, is exactly equal to this side of the equilateral triangle, which is double the length of this leg of my original triangle. So that means that the hypotenuse is going to be exactly double the leg opposite 30 degrees. So it doesn't matter what this is. Let's just call it 1 to make life easy for ourselves. And we can do that because, as we said, we don't care about the size of the triangle. We just care about ratios. So let's pick one with a convenient size. If we call that side 1, then there's no choice in the matter. The hypotenuse has to be 2. Please be sure you understood this argument because it is the key to everything that follows. You might say, well, what if it's not 1? It doesn't matter. Just think about a 30, 60, 90 triangle where the side opposite the 30 degrees is 1, because any 30, 60, 90 triangle will do. That's the whole point of similarity. The ratios will always be the same. So we can decide to use one where this leg is 1. Anyway, if this one is 1, this one has to be 2. And then we've got a right triangle where we know 2 of the sides. Well, forget SOH CAH TOA, here comes Pythagoras. The Pythagorean theorem tells me that if I know 2 sides of a right triangle, I can automatically get the third. And in particular, what's that third side going to be? Well, you remember the little Pythagorean shortcut you met back in the first video, so we don't even have to introduce any new symbols here. That is going to be the square root of what? We know the hypotenuse, so it's going to be the difference of those squares. 2 squared minus 1 squared. 4 minus 1, so that's 3. And we got that by the Pythagorean theorem. And lo and behold, we have now discovered the ratios of the sides on any right triangle with a 30-degree angle in it. In other words, any 30, 60, 90 triangle. All such triangles are similar, and no matter whether they are small or large, we are guaranteed to have the exact same side ratios, even though the individual lengths will differ. For example, let's suppose that on this larger 30, 60, 90 triangle, the leg opposite the 30-degree angle, that is the shortest leg, has the length 3 units. Well, we know that this large triangle is just a scaled up version of this smaller similar triangle. And on this one, we see that the hypotenuse is exactly double the short leg. That means that over here, the hypotenuse is going to be exactly double the short leg of 3. That is, it must be 6 units long. Moreover, we know that on our original here, the long leg is exactly the square root of 3 times the length of the short leg. So the same ratio must hold here as well, because they're similar triangles. That means to get from the short leg to the long leg, I have to multiply by the square root of 3. So I will end up with 3 root 3. And now we have all 3 sides. Same story, of course, with the tiny 30, 60, 90 triangle. If we knew, for example, that its hypotenuse was half, then what would we know about the short side? Well, in any 30, 60, 90 triangle, we know the short leg is going to be half of the hypotenuse. So that means the short leg here would have to be a quarter. And as we said before, we know that on any 30, 60, 90 triangle, the long leg is going to be exactly the square root of 3 times the short leg. So that will be the case here as well, and the long leg will be root 3 over 4. So this particular triangle I've drawn here, this 30, 60, 90 triangle in which the short leg is 1, is a good one to bear in mind. And if you ever forget, well, it only takes about 10 seconds to draw this picture and figure it out. From this picture, which is so easy to understand since it's just half of an equilateral triangle, from this picture, we can immediately read off the values of things like the sine of 30 degrees, or for that matter, the sine of 60 degrees. Well, the sine of 30 degrees, what does that mean? Help us, O great SOH CAH TOA. So, that tells us that sine of 30 degrees is the ratio of the side opposite to the hypotenuse. Well, we see that ratio is 1 to 2. So that's it. The sine of 30 degrees is exactly 1/2. You should understand why this is so, but you should also have this fact firmly in your memory. It should be in there as solidly as 2 times 5 is 10. If someone wakes you up in the middle of the night and says, "What's sine of 30 degrees?" you should be able to say half without any hesitation. You should also be able to say exactly what the sine of 60 degrees is. What is it? Here's 60 degrees. Sine is the opposite over the hypotenuse. The opposite in this case is root 3. Hypotenuse is 2. So sine of 60 degrees is going to be root 3 over 2. Exactly. And if that same person who woke you up so rudely in the middle of the night asks you, "And what is sine of 60 degrees?" Again, you should be able to say without any hesitation, root 3 over 2. Now leave me alone. So be sure you know both of these values. Know them off the top of your head and know where they came from. They come from this picture, which in turn comes from the fact that a 30, 60, 90 triangle is just half of an equilateral triangle. And we are justified in using this particular 30, 60, 90 triangle, where the short leg is 1, because we know that these ratios will be the same on any 30, 60, 90 triangle, thanks to angle-angle similarity. Good. But of course, sine is not the only trig function in which we are interested. We have these other two, cosine and tangent. So what about cosine of 30 degrees and cosine of 60 degrees? Well, let's see. Let's start with 30 degrees. SOH CAH TOA. Cosine is adjacent over hypotenuse. That would be root 3 over 2. So cosine 30 degrees is root 3 over 2. And similarly, we can get cosine 60 by reading off our picture. Cosine is adjacent over hypotenuse. Well, adjacent to 60 degrees, we have 1. The hypotenuse is 2. So cosine of 60 is half. And now you may be thinking, oh, now I have to memorize these as well. These are going to be really easy to mix up because look at the way they switch places like this. How am I going to remember which is which? Well, it's very easy. Remember this if you understand why cosine is called cosine. So let me haul you down here into the basement and I will explain why cosine is called cosine. What does the co tell us? Well, let's suppose that we have a right triangle with some angle theta. Then what do we know about the remaining angle? Well, as we said before, that is going to be the complement of theta, 90 degrees minus theta. Let me give names to the three sides of the triangle. Let's just call them A, B, and then C for the hypotenuse. Now, I want to think about the cosine of our angle theta. In terms of the labels that I've put on the sides, what is the cosine of theta? So CAH TOA, adjacent over hypotenuse. So that would be A is the side adjacent to theta, and the hypotenuse is C. So cosine of theta would be A over C. Okay, simple enough. But now let's shift our attention over to that complementary angle. That same ratio, A over C, if we view it from this other angle, the complement of theta, that would be the opposite side over the hypotenuse. And opposite over hypotenuse, well, that's sine, SOH CAH TOA. So we could just as easily say that A over C is the sine of the complement of theta. And what we've just shown here holds for any acute angle theta. For any acute angle theta, cosine of theta is the same thing as the sine of theta's complement. So I'll just keep that conclusion and write this more compactly. And that explains why cosine is called cosine. Let me write this less symbolically and more rhetorically just to emphasize the point, i.e., the cosine of an angle is the sine of its complement. That is why it is called the cosine. So, for example, we immediately know that, say, the cosine of 10 degrees, forget about its numerical value, whatever it is, it's going to be the exact same thing as the sine of 80 degrees. Or similarly, the cosine of 22 degrees, we know by this little theorem we've proved here, is going to be the same thing as the sine of the complement of 22 degrees, which is 68 degrees. Or the cosine of 50 degrees is, of course, going to be the sine of 40 degrees. This gives us a way of reducing questions about cosine to questions about sine. And of course, we can read it the other way around as well. Sine of 80 is cosine of 10. Sine of 68 is cosine of 22. Sine of 40 is cosine of 50. The sine of an angle can be turned into a cosine if we take the complement of the angle, right? Like the sine of 75 degrees is going to be the same thing as the cosine of 15 degrees. And this little theorem we proved right here is an important one, and we will see two others very much like it in the next video. Of the 6 trig ratios, there are actually 3 pairs of so-called cofunctions that work like this. Sine and cosine, tangent and something called cotangent, which we'll meet next time. And then the remaining 2 trig ratios are called secant and cosecant. So we have these 3 pairs of cofunctions, and they all work in this same basic manner. I haven't even introduced you to cotangent yet, but as you might guess, the cotangent of 20 degrees, whatever that might mean, is going to turn out to be the same thing as the tangent of 70 degrees. So that's to come, but I wanted to point out that this is a pattern we will see again. This is the first instance of it. The heart of trigonometry turns out to be this densely connected web of relationships between the 6 trig functions, sine, cosine, tangent, and the other 3 you'll meet next time, cotangent, secant, and cosecant. They're related in all sorts of interesting ways, and these cofunction pairs are one of the first of those ways that you'll meet. I bring it up here because it cuts down on the amount that you have to memorize. As I've said before, the more you understand, the less you have to remember. Or rather, what you have to remember becomes something logical and coherent, rather than just a collection of seemingly unconnected facts. So let me box this guy up for posterity and tuck it out of the way. Anyway, returning to my point about these special angles. These two facts, the sine of 30 degrees and the sine of 60 degrees, are ones that you should commit to memory. You don't actually have to memorize the cosine of 30 and 60 degrees, provided you understand why cosine is called cosine. Because if somebody wakes you up in the middle of the night and says, hey, what's the cosine of 60 degrees? All you have to think is, oh, cosine of 60 degrees, that's the same thing as sine of 30 degrees. And I know that, everybody knows that. That's going to be half. And similarly, what's cosine of 30 degrees? Well, look, I know that's sine of 60 degrees. And you've memorized that. Sine of 60 degrees is √3/2. So you get those two for free if you understand why cosine is called cosine. And, of course, you have these two facts memorized, which is not hard to do. And if you ever forget them, you can, of course, recover them very quickly by thinking of this picture, which you should also have firmly locked in your mind. And if you ever forget that, of course, you can reconstruct it because it is just half of an equilateral triangle. And the argument by which you produce those values is very straightforward. Great. So now we've got the sines and cosines of 30 and 60 degrees. We have exact values for them. What about the tangent of 30 and 60 degrees? What's the tangent of 30 degrees going to be? Well, let's look at our picture. 30 degrees, and we're interested in tangent. SOH CAH TOA, opposite over adjacent. So it's going to be 1 over the square root of 3. Or if you like to rationalize your denominators, we could do that here by multiplying top and bottom by √3, and we would get √3/3. Though I usually remember this one as 1 over √3. And that's it. That's the tangent of 30 degrees. Oh, by the way, a quick point in passing about rationalizing denominators. One reason why something like this is nice is because you can get a sense for its actual numerical value as a decimal much more easily than you can over here. If somebody asks me, what's the approximate value as a decimal of 1 over √3, well, before I could make any sense of that, I would have to rationalize it, because I know that square root of 3 is in the neighborhood of 1.7. That's just something you should know. Presumably you do know it just by playing around with calculators or something. But anyway, if I'm thinking numerically and I think, well, this is like 1 divided by 1.73, etc., dividing by some nasty irrational number, it's not an easy thing. Whereas if I write it in this form, I can say, oh, well, that's about 1.7-ish divided by 3. All right, well, that's a little less than 1.8 divided by 3, which is 0.6. So this whole thing is going to be something less than 0.6, but probably not too much less. And that's true. It turns out to be about 0.58. I mention this in passing just because I feel like recently I've been encountering more students who don't have much of a feel for the numerical values of irrational numbers. Like everybody knows that half is 0.5, but similarly over here, the sine of 60 degrees, which of course you already have memorized, is √3/2. Well, if you know √3 is about 1.7, half of that is what? Well, 1.6 cut in half would be 0.8, so it's going to be a bit more than 0.85. All right, not the most important thing in the world, but certainly worth mentioning in passing. Just developing a sense for the sizes of numbers is important for anyone who works with such numbers. All right, so we have tangent of 30 degrees is exactly 1 over √3, and we can also get that the tangent of 60 degrees is what? Well, here we are. Here's our 60-degree angle in our right triangle. SOH CAH TOA. Tangent is opposite leg over adjacent leg. √3/1. That is the square root of 3 itself, which again is about 1.73-ish. And so now we have sine of 30 and 60 degrees, the cosines of 30 and 60 degrees, and the tangents of 30 and 60 degrees. We read them all off this one easy to reproduce picture. And you might ask, should I memorize these two facts, the tangents of 30 and 60 degrees? I think it would be wise. They come up frequently. Maybe it's not as immediately vital as knowing the sines, which then immediately gives you the cosines. You can always get them in about 30 seconds by writing down this picture, which, as I said, should definitely be in your mind. Anyway, I'm going to put these in green parentheses as an indication that you should probably memorize the tangents of 30 and 60 degrees. Definitely memorize the sines of 30 and 60 degrees. You don't have to memorize the cosines of 30 and 60 degrees because you get them for free if you understand why cosine is called cosine. All right, and that's it. For 2 of our 3 special angles, 30 and 60 degrees, we now have the sines, the cosines, and the tangents. But I mentioned this other special angle as well, 45 degrees. We got 30 and 60 degrees because they showed up on this very nice triangle, which was half of an equilateral triangle. Well, guess what? If 45 degrees is in a right triangle, then the remaining angle is also 45 degrees, and we have another very special and simple sort of triangle. The sides opposite those angles are also equal. So a right triangle with a 45-degree angle in it is a right isosceles triangle. And whereas a 30, 60, 90 triangle is half of an equilateral triangle, a right isosceles triangle is half of a square, which might make it easy to think about. And as we've said many times, since all right triangles with a 45-degree angle in them have the same proportions, when we're looking for these ratios, it doesn't matter what we take to be the length of any particular side, because we don't care about the size of the triangle. We don't care about its individual side lengths. We only care about the ratios of the side lengths. So we can set any one of those side lengths to be whatever we want. We just have to have the right proportions. So let's go ahead and call the legs 1. We know they're equal. We could call them whatever we want, but we'll make it 1 unit to make life as easy as possible for us. Well, what does that tell us about the hypotenuse? You probably know what the diagonal of a 1 by 1 square is, and if you don't, well, just call on old Pythagoras. We know 2 sides of this right triangle, the 2 legs. So again, without introducing any new symbols, just using those Pythagorean shortcuts from that first video in the series, we know this is going to be the square root of what? We know the 2 legs, so it's going to be the sum of their squares. 1 squared plus 1 squared, which of course is 2. And that's the picture we want to have in our minds. From this very special triangle, this right isosceles triangle, we can immediately write down the sine, cosine, and tangent of 45 degrees. Well, take your pick which 45-degree angle you want to use. Doesn't matter. I'll use this one. Sine, SOH CAH TOA, opposite over hypotenuse. That's going to be 1 over root 2. So sine of 45 degrees is 1 over the square root of 2. Or if you like to rationalize your denominators, root 2 over 2, which again is a useful form because when we write it like that, we understand its numerical value very easily. Because what's the square root of 2 as a decimal? Well, everybody knows, I hope, that the square root of 2 is about 1.4. Cut it in half, and we recognize that this is about 0.7. Nobody memorizes that. You just memorize that sine of 45 degrees is 1 over root 2. And then if you want the numerical value, you think, well, that's root 2 over 2, which is about half of 1.4, which is 0.7. Anyway, what's cosine of 45 degrees? Let's use the same 45-degree angle. Cosine, SOH CAH TOA, adjacent over hypotenuse. That's 1 is the adjacent side over root 2. Hey, that's interesting. Cosine of 45 is the exact same thing as sine of 45. Who would have guessed it? Well, you should have guessed it, because think about this cosine 45 in another way. Think about why cosine is called cosine. Cosine of 45 is the sine of what? Cosine of 45 is the sine of 45 degrees. So of course they're going to be equal to one another. As I said before, trigonometry turns out to be shot through by this dense web of interconnections between the trig functions. And being able to jump from one strand to the next will be the mark of really understanding trigonometry well. So it's good to get in the habit of constantly shifting your perspective and seeing the same thing from multiple angles. On the one hand, you see that sine and cosine of 45 degrees are equal because we can read that right off of the corresponding right triangle. But on the other hand, we can understand that equality in terms of this so-called cofunction identity, which explains why cosine is called cosine. Good. And only one little fact remains. What's the tangent of 45 degrees? Well, that's very easy to see from our picture. Tangent, SOH CAH TOA. Tangent is opposite over adjacent. 1 over 1. So that is 1. Such a nice, simple value. Should you have these memorized? You should. Everybody should know tangent of 45 degrees is 1. In part because the value is so nice, in part because it's so obvious looking at the picture. It has a clear geometric meaning here, which relates to the fact that we're working with an isosceles triangle. You should know that the sine of 45 degrees is 1 over root 2. And then, of course, you get the cosine for free, thanks to this cofunction identity. And so that's it. Even though we have 3 angles and 3 functions, it's not really a matter of memorizing 9 separate facts. Here are 4 that I would say you should definitely have at the forefront of your mind. Make sure you get them there. And then there's 3 that you get for free, thanks to that cofunction identity, and 2 that you should probably memorize. And again, this isn't rote memorization, because you should understand where all of those facts come from. And if you ever forget one, you should be able to recover it in a matter of seconds by drawing the appropriate picture, either half of an equilateral triangle or half of a square. But however you get it into your head, be sure that you can come up with any of these values very rapidly, because in the next chapter, we will expand our collection of special angles at which we can get exact expressions for the trig functions. And when we do that, you need to have all these things at the tip of your tongue, because all the rest depends on this. And if you're stumbling over these basic facts, you'll have trouble getting to the stuff we'll need in the next chapter. Okay, I should mention that in the book, I introduce one other important trig identity related to this stuff, which is this one. For any acute angle theta, the tangent of theta is the sine of theta over the cosine of theta. This is a nice relationship because it involves all 3 of our basic trig functions. It's very easy to prove. I'm going to leave the details to you, but it's very much the same spirit as our proof that we went through for this cofunction identity. We just have a general right triangle with some angle theta in it. Let's just call the sides A, B, and C for the hypotenuse. And I'm going to leave the rest of it to you. All you have to do is get an expression for tangent theta in terms of A, B, and C, and then get an expression for sine of theta over cosine theta in terms of A, B, and C, and verify that they reduce to the exact same thing. This is often a handy identity. We'll put it to use more as the quarter goes on. And it's tempting to think, hey, if I know that, then I don't need to memorize, say, tangent of 60 degrees is root 3, because I could just get sine of 60 degrees, which everyone knows is root 3 over 2, over cosine of 60 degrees, which is, well, let's see, that's sine of 30 degrees, which is a half. And then when I reduce that fraction, everything works out to square root of 3. That is true, but it's a little bit of a pain. Not so much when the whole problem is to find tangent of 60 degrees, but if you're aiming towards something larger and you just very quickly need to know what tangent of 60 degrees is, it's nice to just know it's square root of 3. But enough about that. Let's move to the last big topic of this lecture, which is the right triangle trigonometry machine. As promised, I can now show you how to operate the trigonometry machine on right triangles. Turns out it is very easy once we understand the meaning of sine, cosine, and tangent. So let's start with an example. Let's suppose we have a right triangle and enough information to determine that triangle. So let's say, for example, we have angle, side, angle. We know that's enough to determine the triangle. So let's write down the information. Well, the first angle we know is 90 degrees. Let's say this side is 8 units, and let's say this angle is 37 degrees. So as we learned in the previous chapter, we have enough information to determine the triangle. So we should be able to figure out the 3 missing parts. Traditionally, this is known as solving a determined triangle. When we have enough information to determine the triangle, solving the triangle just means finding the missing parts. Anyway, let's solve this triangle. We'll start with the easiest part, the missing angle. Of course, it is the complement of the other acute angle. Well, 90 minus 37 is 53 degrees. All right, that part was easy. The interesting part has to do with the sides. How do we find the missing sides? Pythagoras doesn't help us because we only have one side of our right triangle. But SOH CAH TOA will help us. And so we pray, O great SOH CAH TOA, I desire to know this side, A, which is opposite 37 degrees. But the only other side I know is this one, 8, which is adjacent to 37 degrees. What must I do, O great SOH CAH TOA? And he answers, Hearken unto my name. You wish to relate the legs opposite and adjacent to 37 degrees. SOH CAH TOA, tangent is what relates the opposite and adjacent legs. And we thank great SOH CAH TOA for his immortal wisdom. And we write down that the tangent of 37 degrees is indeed the opposite over the adjacent, and therefore A over 8. Now that equation will give us what we want, because all we have to do is solve for A, which is easy enough. So that equation implies that A, the thing we want, must be 8 times the tangent of 37 degrees. And that is the exact value of A. And some people are initially uncomfortable with that because this looks like a problem problem to be solved, but this is the same way that sometimes people are initially uncomfortable with something like the square root of 7, which is an exact value. We can ask for its decimal approximation, but that is an exact value in and of itself. So here's the exact value of a, and if we want a decimal approximation, we will have to consult Texas Instruments, or Casio, or whoever makes the calculator you use. When we type that into our calculator, we get about 6.03. That is, of course, an approximation, hence my wiggly approximate equal sign. Good, we have disposed of side A. All that remains is C, and you might be tempted to use the Pythagorean theorem here, and that would be okay. I would just advise you, if you're going to use the Pythagorean theorem, to watch out, because you already have an approximation, and if you feed an approximate value into some other algebraic expression, the round-off error that we have right here can get magnified. So either take lots of decimal places before you do it, or just use this expression algebraically and don't do your rounding until the very end. But if you don't want to mess around with that, or if you just want some more practice, calling on SOH CAH TOA, we could do it another way. We could say, I'm looking for side C, SOH CAH TOA, what do I do? I know this angle 37 degrees. I know the adjacent leg, 8. How do I relate the adjacent leg and the hypotenuse? And SOH CAH TOA, once again, says, hearken unto my name. SOH CAH TOA, cosine relates adjacent and hypotenuse. Ah, thank you, great SOH CAH TOA. Cosine 37 degrees is going to be adjacent leg over hypotenuse, 8 over c. Well, that implies that c is going to be what? Well, when we solve this equation for c, we end up with c is 8 over the cosine of 37. And naturally, we would like a numerical approximation for that. And my trusty TI-36X Pro tells me that it is about 10.02. And we are done. We have solved this triangle. We have used the trigonometry machine to produce the missing sides. Of course, the missing angle, but that was easy. And that's about all there is to it. A couple of quick observations. First, there's often several ways you could set up a trig ratio like this to solve for a missing part. For example, think about when we were looking for c, the hypotenuse. We did everything in terms of this 37-degree angle, but we could have done it in terms of 53 degrees. We could have said, I'm going to use this 53-degree angle, I know the opposite leg, and I want the hypotenuse, so I'm going to use sine opposite over hypotenuse. And then I would have had sine of 53 degrees is 8 over c, from which it follows that c is 8 over the sine of 53. And when I run that through my calculator, I get, of course, the same 10.02. So same conclusion, of course, but slightly different path because I used sine. Hey, but you know what? Look at these two equations we set up to solve the problem. Notice that the right-hand sides are the same in both cases, 8 over c. But look at the left-hand sides. Cosine of 37 and sine of 53. They look different, but are they really? No, they are not, because you know why cosine is called cosine. Cosine of 37 degrees is sine of 53 degrees, because cosine of an angle is the sine of its complement. Good. I want to just keep reinforcing some of these ideas wherever we can. Okay, so now you know how to use the trigonometry machine almost completely for right triangles. There's one last thing I need to mention. This shows you what we've just done so far, how to find any missing sides you might need. But the angle we got here was a little cheap, because if you know two angles, then of course the third one you get for free since the sum has to be 180. But it's a little different if we don't have either acute angle. So let me give you one example like that. Here's a right triangle where we know all three sides, 3, 4, and 5. This is a famous one because it's rare to have a right triangle where all three sides are whole numbers. But anyway, since it's such a famous triangle, we would like to know the angles. We can't get them in the cheap way. I know I've got a right angle, but what are the other two angles? Pythagoras has nothing to tell me. He just talks about the sides. How am I going to get those angles? Well, if I know one of them, then I automatically know the other because of course they're complements. So let's just give one of them a name. Let's call this one over here alpha. All I need to do is call on SOH CAH TOA, and I ask him, great SOH CAH TOA, how can I find this angle alpha? And he looks back at me, and he listens to my prayer, and says, you fool, it's simple enough. Use any part of my name. For example, you want this angle. You know the adjacent leg. You know the hypotenuse. Use cosine, you utter fool. SOH CAH TOA is getting impatient with my calling on him over and over again. But that's okay. He's right. I could say that the cosine of alpha is 4 over 5. But then I appear to be stuck, because I'm not just interested in the cosine of alpha. I want to know what alpha itself is. How do I get alpha disentangled from its cosine? Well, fortunately, just as your calculator has programmed into it the cosines of any angle you care to put into it, it also has the inverse process. If you tell it, I want to know the acute angle whose cosine is 4/5, it will tell you. So I have to introduce you to the notation for that, which unfortunately is not good notation. But this is what it is. We would say that alpha is this horrible expression. We read that as inverse cosine of 4/5. It's terrible notation because this looks like it should mean something like 1 over cosine. That is not what it means. It's an easy point of confusion, and I sympathize with you because it is bad notation. What this means is inverse cosine of 4/5, which effectively means the angle whose cosine is 4/5. And that's what we're looking for, because that's what this is. This is the angle whose cosine is 4/5. There is some subtlety to the idea of inverse trig functions that we will talk about when we get to chapter 13. But as long as we are just talking about solving triangles, there's no subtlety at all. So for now, we can just think of this as meaning the angle whose cosine is 4/5. And you will find somewhere on your calculator the appropriate buttons with which you can enter this expression. When I do it on mine, I get approximately 36.87 degrees. And once we know that angle, of course, the other one is just going to be its complement. So if I call the other one beta, then we know that beta is going to be 90 degrees minus alpha, which is approximately 53.13 degrees. And that's it. We have found the missing parts of our triangle. And you now know how to use the trigonometry machine for right triangles. In chapter 11, we'll extend it to the case where you can use it for any triangle whatsoever. One final note I should mention about calculators. If you were following along with this and you reached a point where what came out of your calculator was not the same as what came out of my calculator, it's probably because you have your calculator set in the wrong mode. You'll have to look up how your calculator works, but there's generally a way to toggle between a degree mode and a radian mode, and then usually something called a gradient mode, but nobody uses that actually. If your calculator was producing different values than mine was, then you probably have your calculator set in radian mode. Figure out how to switch it back into degree mode, which is where we'll keep it for the next few chapters, and everything should work out the same. Okay, be sure you learn all this stuff well, do the homework problems, and I'll see you next time.